one that says has a little camera. Okay, so we have. May I borrow that, please? Okay, so Isaac 3 covers Isaac Newton's third law of motion. Our objective, students will demonstrate Newton's third law of motion, interaction, equal and opposite reactions. Students will model the flight of a rocket and test variables. And this one doesn't have a lot of variables in it, so I'm going to turn this, as mentioned in the first two videos, taking a simple lab and even adding more to it to make it more complicated. If the force acts on the object reacts with equal force, and we're going to see that. And this is a pretty classic little experiment with the taping the inflated balloon to a straw and then letting it go and it traveling along the string. Our procedure and results, of course I'll film this too, and I'll try to put a copy down at the bottom in the description. Long balloons, I think the closer we could get on this. String, tape, straws. We got a couple chairs that we're going to use to tie the strings across. Inflate a long balloon and release it. Observe what happens. Of course, we're going to repeat this and actually make a data table this time on our observations. It's going to be. We're also going to go back and review the film and see how long it takes. Use the camera's clock and see how long it takes each balloon to get scrubbed. And do it 3 times and calculate it. And we'll measure the distance and calculate the speed of each balloon. The chair on one side of the classroom, inflate the long balloon and tape it to the straw. Of course, we've got to put the string through the straw before we tie it to the chair. It's one thing they don't tell you on here. So put the straw through on the string first, then tie it to your chair so it's able to slide back and forth. We'll also need tape to tape the balloon to the chairs. And then we'll repeat it. And on this one of the variables, okay, this is one variable we're going to do is 3 different kinds of strings. But they also want you to vary the angle of the string, probably up and down this way, as opposed to sideways. But we'll do them all. But we'll look at one at a time. First thing we're going to do is see which one of these 3 does the balloon travel along best first. So we'll make a hypothesis. Here you go. And write down the first hypothesis. I want you to make a hypothesis. Twine. Look here, we got twine. Kite string. And fishing line. So these are 3. What's the difference, do you think, between those 3 types of strings? And the twine, a kite string, and the fishing line.
They all have different thicknesses.
Different thicknesses? And there's one difference. What's another difference? You've touched each one of these, right? What's the difference of the way each one of these feel?
Well, they're different materials.
Okay, what's the difference between the way
Roughnesses.
different roughnesses? How might that affect how well the straw with the balloon attached to it slides down?
The rougher ones, it might be harder to slide. Yeah.
So, in your hypothesis, I want you to write down which one do you think, which of these strings our rocket balloon would travel down the fastest, and explain why. Remember, it's not just a guess. You should have a good, reasoned out, logical answer. a hypothesis. So explain why, say which one and explain why you think that. Pause. Yes. All right. So first part of the lab here, the activity, was to blow up the balloon and just let it go and observe what it does. And let's do that. Okay. So, what did it do? Did it travel in the straight line? Did it go up?
It did travel in a straight line. Yeah, it kind of went in a circle and then...
Was that a circle? But what do you call a circle that's moving? Something that moves in a circle.
Spiral.
So it spiraled, right? Now does it do that every time? I don't know.
One time it just fly across the room. Just big enough.
Not necessarily exactly the same every time. But kind of.
Yeah.
All right.
Not exactly.
So we're going to...
Exactly the same.
These should be the same size. 3 times first. We're going to do each one 3 times to repeat our experiment. And we'll go back and actually watch the film later. It's nice thing about filming experiment. You can use a timer, but if you film it, you can go back and look at the clock, and and we'll measure the distance and watch and write that down in a minute. Tape measure.
Free filming.
Okay. There's something else I need to make sure of. We'll make sure we control our other variables, right? What I need to make sure of that's consistent with the balloon every time I blow it up. Am I going to get the same results if I blow it halfway up versus all the way?
You need to blow it up the same every time, or about the same.
Pretty close to the same?
Yes.
How do I make sure I can do that?
If you measure how big you blow it up.
Measure how, with what do you think?
A tape measure?
What kind of tape measure?
Yeah, measure one drawing long and way. Flexible. Flexible.
Flexible, like a tailoring tape measure? Okay. Go ahead and pause, please. Piece of tape on here. It's easier to put it on here and bring it back. That's not as big as the other one I was using. This won't work.
There's the biggest it gets.
So if we measure the length of this, that should be about right. I'll just use the measure length because since the pressure and the air pressure should push pretty uniformly on the same on all these. As far as shape goes, we'll use the length as a as the measurement to determine if they're all the same for the other ones.
Why not use the circumference?
Because it's hard to do with one hand, and it's easier to do this. The air should be pretty much uniform pressure every time. There will be little variances because of temperature and whatnot, but it's not going to be that big. Okay, could you pause, please? Okay, it's about. I'm holding it to the end. So about 23 centimeters. Okay, pause please. Okay, so now we'll take the center here, tape it, pull it back as far as we can. Didn't go anywhere.
Yes, it did.
Not very much, so
It did go somewhere.
let's see this. Centimeters. Take it back in here, we'll pull it back, and
It always goes to that same spot.
this it came off. That's pretty close. Another piece of tape, please. Tape might need to be a little longer. Can you give me another one, please, that's longer than that? Thank you. Okay, so
That one didn't even go.
I guess I go ahead and use the same balloon for this. So much for the twine. Another piece of tape, please.
Pause it.
Just let me get this balloon. It won't film anymore?
It's filming again.
So, attach this. And go ahead and pause. So you can see we had to stop for the day and continue this the next day. Now we're trying to kite string.
Okay.
And this is actually what I originally called for. So it's, 23. Attach this.
Maybe you have it too close to the other string and the balloon touches the other one.
Shouldn't matter. Yeah, I've done this before and it's actually spiraled around the string.
When you did it before, did it go all the way across the kite string?
Yeah, I've had it.
Have
know what
had to
this
go all
does
the
for
way
the
across
classroom
the
and had it
twine?
go all the way across. So.
Have you ever had to go all the way across the twine?
Yes. Oh, the twine, no. I've never done twine. That's the first time I've done the twine. I didn't know what was going to happen with that. Okay, there's number 2.
Are you filming?
Yes, we're going to film.
Let's
Your
change
silly
it
voice.
to a little dee-dee-dee-dee-dee feed.
Now, see, this how when you actually try some of these in real life, this is about how it works out. If you think it's silly to wear safety goggles with balloons, but I actually had a student that ignored the safety rules one time, years back. Didn't put their safety goggles on, after being reminded. They were blowing up the balloon, and it popped and hit him in the eye. Luckily, it didn't actually, stung, but it didn't actually do any damage. Maybe these straws too. That actually got further down that time, at least. The second part of the Alright, made it all the way to the end that time. Fairly quickly. So we figure out which one works the best to actually get it making this work. I'll make the second part of the experiment that much easier that we're using the proper line to conduct the experiment. And I think it actually suggested, if I remember correctly in the directions, to use kite string. See, it still has enough friction in it to work that well. This is also easier when you've got someone to hold this stuff, or you got a partner to help you. Try that again one more time.
Oh no.
That's it. Now, just go ahead and pause. It has the less friction, works the best. Part of the issue I found with doing these experiments like this is, of course, as the balloon deflates, you got the tape stretch on, as the balloon deflates, it pulls. And if it's not even, or not, one side will pull more than the other one, and then it tries to veer off and then go sideways. So that causes other complications. Let's try a longer piece of tape. And sometimes part of an experiment, or design experiment, to get it to work, is also your experimental setup. So, do I got the right kind of balloon? Am I putting the tape in the right spot on the balloon? I try to do in the middle. Doesn't need me toward the end, toward the front, or toward the end, or right in the middle. Which one of those works the best? A short piece of tape versus a long piece of tape. On one side, you would think it needs to be balanced. There's other variables that could be affecting the results and the success, whether and how well this works, if it works at all. It's always a nice concept on paper. People come to think of this, and then a lot of times when you try it yourself, it's not working out as well as what they said. Like that, and that didn't go anywhere. It will slide. We know what it's supposed to do, but this may be enough tension. Try it again. What kind of energy do we have in this balloon right now? Without this potential energy, and when I let go, that potential energy is converted to what kind of energy? Kinetic, right. And part of it, as when the girls point out, like I said, this wasn't in the way. I've actually had them go down, but then they'll spiral around the string as they're going, so they won't necessarily go straight down in a straight line like a so I'm using a longer straw. I'm going to use 2 pieces of tape. Hold this on here. Unfortunately, when you do it by yourself, it's a little difficult. So we're going to do 3 times straight, then I'm going to raise the string up a level, so we've got an angle going up. We'll let it go up 3 times, and then we'll just go the opposite direction for the downward direction, and compare the speed of them 3 times. Alright, worked it much better than it did last time. Actually working the way it's supposed to. It did go around. You see how those other strings might get in the way. Probably the best thing is just take this tape off totally every time. Just put it back on when I'm done. Out anything, but it did sting. And it twirls around, so that's part of it. Does that sometimes, part of the reason the other strings were getting in the way before, because it has to allow some freedom of movement. We'll put that down here real quick. And we're going to pause the film by. Okay, now we're going to. So it goes in an upward slope. Our standard comparison was our horizontal. Now we're doing upward, and to do downward, I'll simply turn the balloon down, and I'll just have it go this way. And it's going to be hard to note the difference in speed. Goes pretty fast. And see, especially at short distances in a setting like this, with a stopwatch, it's going to be really hard for kids or adults to get that timing down, to start and stop it in the amount of time it takes accurately or with precision. So with filming your experiments, you can go back and use that as part of your technology. It's part of it if you're most states lessons, part of their objectives is use of technology in science, and that is technology. And you can sit there, slow something down, and see things at a slower speed, or pause it that you couldn't see just by eyes alone. Do it one more time. If we really wanted to be accurate, we do it more than just 3 times. And of course, higher the grades, the more they should be repeating experiments. So this is more of a 6th grade, beginning middle school level type of thing. That looks like it's quite long, I know. Okay. 3 times. Well, let's see if it gets any faster going the other way. Going downward now. Now, ideally, you want the kids to do this. What did you observe? Okay, let's pause. Pause.
Well, I didn't remember the exact speed of last time, so.
Well, we're going to use it to go back and review the film, so we can also compare it. Look at the clock on the film to compare the time. So.
That was faster.
Does that look faster?
Mm-hmm.
I'll have to look at the film because I'm having a hard time telling the difference. That's pretty close. It's upside down. That's right. One more time. some of them, some experiment, they'll do the same thing, but they'll have, we mentioned that before, they'll measure the circumference of the balloon. Since the air pressure is pretty evenly pushing all parts of the balloon evenly, hypothetically, it should work just as well just to measure the length of the balloon. If all your balloons make the same shape that you're using, so you can use that if you don't have a flexible tape measure. Came off. We'll have to repeat that one. I didn't know it was all the way down. That happens sometimes. Air temperature and other variables are negligible, so we're not really worried about that, though. Realistically, if you really get detailed, you would count that in here. This is messed up.
Want the straw?
And that's it for right now.
And this is the paper for Isaac 3. So we get this in focus. Listing out the objectives and our questions we answered. And this is it. There's not a second page. If there's any questions or suggestions, comments, please leave them down in the comments section below. And thank you for your time and attention.